We are in chapter 4 where we are discussing bending. This is the 19th session overall and we continue discussing bending moment and shear force example. Here we discuss a hinged beam. This is the overall roadmap with sessions covered in the first 4 chapters. We are looking at bending moment and shear force diagrams over a few sessions. We earlier discussed about a cantilever beam. A cantilever beam has one fixed end and another free end. Considering that there are no horizontal forces, there are two unknowns, the vertical reaction and the moment at the fixed end. There are also two equations of statics, and as such, a cantilever beam is statically determinate. Now consider this case. Here there's a support at B, and hence there are three unknowns, but we still have two equations from statics. So this case is statically indeterminate. We will develop the shear force diagram and the bending moment diagram for this problem. There's a support at B in this case. However, there's also a hinge at E. This problem is statically determinate. We now concentrate on the hinge at E, and for that we recall our discussion on plane frames. In order to analyze plane frames, we considered equilibrium of the individual members. Thus, we considered equilibrium of our members such as ABD and ABC. Now, let us look at the equilibrium of the pin at B. Now, the pin at B is subjected to a force due to ABD. It is also subjected to a force due to EBC. The pin is in equilibrium, so the forces due to these two members must be equal and opposite to each other. The pin B in turn exerts forces on the member ABD and EBC. So the pin will exert an equal and opposite force to the member ABD and an equal and opposite force to the member EBC. Now we do not know the direction and magnitude of these forces. So we represent these forces in terms of a horizontal component and a vertical component. Here the force acting on the member ECB due to the pin at B is shown, and we have taken the direction of RBY and RBX arbitrarily. Now, since the forces that these two members exert on the pin are equal and opposite, the forces that the pin in turn exerts on these two members has to be equal and opposite as well. So here we see the force that the pin exerts on the member ABD. So the magnitude has to be the same as the force that B exerts on ECB. So we can say that the horizontal and vertical components would be equal and opposite. So since we have taken RBY upwards here, we have taken RBY downwards here, and RBX is on towards the right and RBX here is towards the left. Now this problem is similar with the hinge between two members. Also, there's no horizontal forces acting in this case. So the hinge at E will be in equilibrium due to a force to EB and also a force due to AE. These forces will be vertical forces and equal and opposite to each other. The hinge E in turn will exert opposite forces on EB and AE. So these forces also will be vertical and equal and opposite to each other. To solve this problem, we will separate the two parts AE and EB and consider the equilibrium of these two parts individually. The force that acts on EB due to the hinge is chosen, the direction of that force is chosen arbitrarily. But we know that the direction acting on AE will be equal and opposite. On the whole, due to the hinge, we have added one unknown, but we have also added two extra equations. As we did in the case of a plane frame, we'll now consider the equilibrium of EB separately. So if we take moments about B, then RE into this distance, which is 3 meters, is equal to 18 into 2 meters, from which we get RE, which we get as 12 kilonewton. Then summing up forces in the vertical direction of the beam EB, we get RB as 6 kilonewton. So now we have the external reactions acting on the beam EB. The direction that we had arbitrarily chosen of REY has turned out to be correct. So that means that the REY will act in a downward direction on AE. So we know the magnitude of REY. So this becomes a cantilever problem. We then use equation of statics to find out RA and MA. This load is triangular and the total load is given as half base into height, that is half 10 into 3, that is 15 kilonewton. So RA would be equal to 15 plus REY, which is 12, that is 27 kilonewton acting upwards. One would notice that here we are acting from the right side. So the downward is positive. Similarly, we see that REY and this triangular load will create a clockwise moment from the right. So the moment that they will create would be negative as per our convention. The resultant of this triangular load acts through the centroid, which is located at 2/3 distance from of the base from C, that is at 2 meters, which means that the distance of the resultant of the triangular load is 4 meters from A. So we get the moment MA as 15 into 4 plus 12 into 6. And since the moment is clockwise from the right, the moment is negative. As earlier mentioned, to find out the shear force and the bending moment diagram for a beam, we take sections where the pattern of loading does not change. So here in AE, we have taken 3 sections, and in EB, we have taken 2 sections. Consider section 1-1, and the shear force acting is 27 kilonewton, and the moment acting is minus 132 plus 27x. In order to find the shear force and bending moment corresponding to section 2-2, we need to know the total load due to this truncated triangle and the position where the resultant acts. This whole triangle is represented by this dotted triangle. So this dimension is 10 and this dimension is 10. CD is 3 and this dimension is 3. Section 2-2 is at a distance x from A. Now AC is 2. So this distance is x minus 2. This means that this ordinate is 10 divided by 3 into x minus 2. The area of the shaded triangle is this ordinate into x minus 2 divided by 2, which we represent here. The position where the resultant acts from C is 2/3 of x minus 2. Now AC is 2, so the distance of the resultant from A is 2/3 x minus 2 plus 2, which is equal to 1/3 x minus 2. So now we have the magnitude of the resultant and the position where it acts. So the shear force acting on section 2-2 is 27 minus the magnitude of the triangular portion, which we get by this expression. Here we have expanded x minus 2 square. The bending moment at section 2-2 is minus 132 plus 27x minus this magnitude into this distance, which you have represented here. Now carrying out some algebra, we get mx as shown here. We now find the shear force and bending moment at section 3.3. The total load of this triangular portion is 10 into 3 by 2, that is 15. So the shear force at section 3.3 is 27 minus 15, that is 12. The 15 kilonewton load for this whole triangle acts at 2/3 distance of CD from C, that is at 2 meters. So the distance at which the resultant acts from A is 4 meters. So at 3,3, the moment is minus 132 plus 27x minus 15 into x minus 4. Now consider section 4.4. The shear force is 12 and the moment is 12 x dash, where we have represented the distance of the section 4.4 from E as x dash. Now consider section 5.5. And the shear force is 12 minus 18, that is minus 6 kilonewton. Now the distance of this load from E is 1 meter. So the moment at section 5.5 is 12 into x dash minus 18 into x dash minus 1, that is minus 6 x dash plus 18. In our discussion till now, a fair bit of concentration was on the hinge at E. Thus, we discussed the forces that act on the hinge at E due to EB and AE. We also discussed about the reaction forces due to the hinge on EB and EA. This helps us to understand the nature of forces on problems such as these with hinges. Our problems with hinges can be treated in a more straightforward manner. The fact that there's a hinge at E means that there cannot be any bending moment at E, since E cannot sustain any moment. Thus, if we approach E either from the left or from the right, finding the bending moment at E has to be 0. So in this case, there are 3 unknowns: the reaction at B, the reaction at A, and the moment at A. There are also 3 equations, the 2 equations from statics and the additional equation that the bending moment at the hinge at E is 0. Hence, we can solve for the 3 unknowns. With shear force diagrams, we realize that there's no change in shear force as we approach from 3.3 to 4.4 section. With the bending moment diagram, we will see that the bending moment we get at E is 0. Earlier, we took 5 sections to find out the variation of shear force for the entire beam, as well as the variation of bending moment for the entire beam. At section 1.1, we found the shear force to be constant at 27 kilonewton. So at A and at C, the shear force is 27 kilonewton, and which is represented by a horizontal line in the shear force diagram. The shear force in section 2.2 was represented by this expression. So we substitute x is equal to 2 and we get the shear force as 27 kilonewton, and we substitute x is equal to 5, which corresponds to the point B, and get shear force as 12 kilonewton. The shear force at C taken in two different ways matches, and which serves as a check that the equations are right. The variation of shear force between C and D is quadratic. So we have represented the variation using a nonlinear line. At D and E, the shear force was found to be constant at 12 kilonewton. At D, the shear force is obtained in two different ways and match, which serves as a check for particularly this expression. Between E and F, the shear force is also 12 kilonewton. So we have taken the ordinate at D at 12 and F at 12, and the shear force is given by a horizontal line. Between F and B, we find that the shear force is minus 6 kilonewton. So between F and B, the shear force is represented in this diagram as minus 6 kilonewton. So here we have the whole shear force diagram considering all the 5 sections. Here we develop the bending moment diagram for the given problem. So between A and C, we found that the bending moment was given by this expression. Now substituting x is equal to 0, we get the bending moment as minus 132. So at A in the diagram, the bending moment has been represented as minus 132. Substituting x is equal to 2, we get the bending moment as minus 78 kilonewton meter. Now x is equal to 2 corresponds to the point C. So we have plotted the bending moment corresponding to the point C. Also, this variation is linear. So we have joined the point corresponding to A, that is the bending moment corresponding to A, and the bending moment corresponding to C by a straight line. Let us now look at the bending moment between C and D. It was given by this expression. Substitute x is equal to 2 in this equation, we get the bending moment as minus 78 kilonewton meter, which corresponds to the point C. Substituting x is equal to 5, we get the bending moment as minus 12, which corresponds to the point B. The fact that we have found out bending moment at C in two different ways and that the match serves as a check. The bending moment variation between C and D is cubic, And here we have given the bending moment using a nonlinear curve. We now look at the bending moment between D and E, and it was given as using this equation. At D, the bending moment was found as -12, and at E, the bending moment was found as 0. The fact that the bending moment at D found in two different ways match again serves as a check. The bending moment variation between D and E is linear as shown, and we have drawn a straight line joining the bending moment corresponding to D to the bending moment and the bending moment corresponding to point E. We found the bending moment between E and B separately. The bending moment between E and F was given as 12 x dash, where x dash was the distance from the point E. So at x is equal to 1, the bending moment was 12. The variation is linear, so the bending moment at E and the bending moment corresponding to F has been joined by a straight line. Between F and B, the bending moment was given by this expression, where x dash again is the distance from the point E. At x dash is equal to 1, from this expression we get the moment as 12. At x dash is equal to 3, we get the moment as 0. The variation is linear, so we have joined the moment at F with the moment using a straight line. So now using the expressions of all the 5 sections, we have given the entire bending moment diagram. Here we notice a few things looking at the shear force and the bending moment diagram for this problem. Earlier we dealt with uniformly distributed load, and we found that the shear force corresponding to the uniformly distributed load was linear and the bending moment was quadratic. Here from C to D we have a triangular variation. We find that the variation of shear force between C to D is quadratic and the variation of bending moment between C and D is cubic. A uniformly distributed load can be considered to be a constant variation, while a triangular variation of load can be considered as a linear variation. We also see that where this point load acts, there's a drop in the shear force diagram. This we have seen earlier. The shear force passes from a positive value through 0 to a negative value. The shear force passes through 0 at F, and looking at the bending moment diagram, we see that the maximum positive bending moment is also at F. We had discussed this issue earlier.